Hello, back for some more modern algebra, made easy. As requested, we got another video. This time it's on factor groups. And by the way, thanks for all the support, guys. If you watch the videos and left comments and stuff like that, really appreciate it. And even that one pushy guy who keeps asking me to make more videos, it actually, gets me to do stuff. So I like that, and it gets me thinking. So I appreciate it. So anyway, we're going to be talking about factor groups today, and this lecture, wow, this topic, wow, it's really interesting. It occupied so much of my mind, like for so many days, I can't even tell you. Like in preparation for this video, I really spent a lot of time trying to work out all the little details, and it's really interesting, and it's really easy, but not at first at all. It's not easy until some things just need to click. And only thing I can say is just try to read as much as you can and study as much as you can, work as many problems as you can, and hopefully things just start to click. But it is very interesting. So just as a review, the way we're going to start real quick is just show what cosets are, because that's a huge part of factor groups. Factor groups, in fact, are cosets. So remember that cosets in a partition a group. So if we have this group here, the integers, then we could write these four cosets. And notice they partition the group. And by partition I mean the union is the group. And also there's no overlap. That's also in the definition of our partition. They can't have anything in common. So notice that these four cosets here, they're not just cosets, but they actually form a group. And I'm not gonna prove that, but I'm gonna try to convince you of that. And that's the whole crux of the idea of factor groups. That's the whole idea of factor groups. So, remember, to be a group, it's got to be closed, right? And it is closed. 4 times an integer plus 2 plus 4 times an integer plus 3, that's 4 times an integer plus 1. Right? So the elements are closed. Like this right here, this is an element in our factor group together, 4z plus 2. It's not this is an element and this is an element. No, together it's an element. So this element plus this element is this element. So it's closed. It's also associative. It doesn't matter what order you add the elements. Like whichever order we add 4z plus 2 to 4z plus 3 to 4z plus 1, we're going to get 4z plus 2. We're going to get a multiple of 4 plus 2. It doesn't matter which order. Which should be, pretty intuitive since we're talking about addition. And what's the identity? Well, the identity is just 4z. The identity is that's the element at which you add to any other element to get that other element. And what's the inverse? Well, the inverse of 4z plus 3, that's 4z plus 1. You add those together, you get the identity. And another thing to note is that the identity is the subgroup itself. So we're going to talk about this again and again. So I'm going to try to give you multiple chances to understand the material. So the way we write this factor group is z mod 4z, and it's in the form g mod h. That's what we say a factor group is, in the form g mod h, like some group modded by the subgroup. Which again should make more sense in a little bit. So the identity of the factor group is the subgroup, and that's always true. So just remember that. So factor groups, also called quotient groups, by the way, notice that all these cosets contain all the possible quotients when dividing by 4. At first it seems like, okay, we just call it factor groups. I have no idea why, or quotient groups. I have no idea why, but if you think about the word quotient, at least, it kind of makes sense. Any number, when you divide it by 4, you're going to get an answer that you can put in one of these forms. And as we just showed, they make a group. So these quotients, these four quotients here, they make a group. So it's a quotient group. That's the term. Sometimes it's not intuitive why the term is called what it is, but in this case it is. So here's my kind of like tiny definition of like an informal of what a factor group is. It's a group G mod H where H is a normal subgroup of G, and I haven't even talked about what it means for a subgroup to be normal. It's a minor detail, but we'll go over it in just a moment. So just as a heads up, cosets may not always form a group. Just because they're cosets doesn't mean they form a group. They gotta be normal. Cosets have to be normal. Okay, so here we go. This is what normal subgroups are. Alright, so elements in a factor group are cosets of G. And they look like G big H. Where H is just big H is just any element in H. And so now a subgroup H of G is a normal subgroup. And by the way I write H being a subgroup of G is just this H is less than or equal to. I think that's pretty standard notation. Anyway, but that just means H is a subgroup of G. So that's normal if GH equals HG for all G in G. So, as I stated earlier, H is just any element in H. And just to break down what GH equals HG means, well, those two are sets. So we're talking set theory. So that means that these two things are true, that GH is a subset of HG, and HG is a subset of GH. So G big H, that means that for G big H to be in HG, that means for all elements H in H, that GH, that product, is in HG. And you don't need to worry like 1,000,000% about understanding it right now. It's not an issue, but I think by the end it will make a lot of sense to you. So it turns out that if the subgroup is normal, then its cosets form a factor group. So I think I said it earlier, cosets aren't always a group. So the cosets have to be together a subgroup, and also they have to be a normal subgroup of a group G. In that case, they're a factor group. And by the way, there's a proof in the book. If you can't find a proof, just Google. If a subgroup is normal, then its cosets form a factor group. You'll find something good. If not, let me know. And by the way, the operation here is kind of interesting. These are two elements. These are two of our cosets. These are two of our elements in the factor group. AH is an element. BH is an element. And that equals ABH. That's the way we compute these is we just do the operation in G, because this turns out to be just ABH. So AHBH is ABH. So this AB here, that means A star B, where star is the operation in G. And this should make kind of intuitive sense, because after all, the subgroups are normal. So AH, if you just flip that around, that's also HA, since it's normal. And then you can just combine AB there as one, and then flip the H's around. Anyway, going a little bit off topic a little bit, but just kind of trying to elaborate on why that operation is the way it is. But for now, just memorize it. And something you should know is that every abelian group is normal. Since GH is HG for abelian groups, then G big H, where is it? G big H equals HG for sure. Now, is every normal a group abelian? Is every normal a group abelian? Well, every normal group is not abelian. So if you want, you can think a little bit more about that, but you can also just memorize that for now. So we're going to start this off with a computation. Find the order of the factor group. This right here, this is the factor group. Z8 cross Z2 mod the cyclic subgroup generated by 2, 1. So G is Z8 cross Z2, and our subgroup is the cyclic subgroup generated by 2, 1. So the order of Z8 cross Z2, that's just 8 times 2, that's 16. We went over that in the previous video. And I think it was in the direct products of finitely generated abelian groups. And then the order of the cyclic subgroup generated by 2, 1 is 4, and I showed that here. And again, this is just a review. We've covered this material before, and I try to make my videos where it kind of builds on itself. Modern algebra, it's really easy to do that because everything just naturally builds on itself. Okay, so Z8 cross Z2. So the way we can get the order of our factor group is just take the order of our group and divide it by the order of our subgroup. So since we already found those two things, the order of our factor group is 4. So this means that our group consists of 4 cosets. So remember, our factor group is cosets. They're cosets of our subgroup. So it will take 4 cosets of size 4 to partition the group. In other words, our factor group will have 4 elements. So if you want to find them, pen and paper, go for it. It's a good exercise. Simple, yet important detail. Okay, this is something that really, to me, is important, but I never saw it mentioned anywhere. And it's if we have a group G, where the set G defined on the binary operation star, and we're going to let a little g be in G, is little g big G equal to G? That is the coset little g big G equal to G? I asked this to one of my professors, and he just laughed at me and said yes. And I said, okay, I get part of it, but how about the other part? And he says, let me show you. And I said, okay. And so now I'm going to show you. So to show that two things are equal, we have to show that they're subsets of one another once more. And it's pretty easy, the first part of it. Like, for instance, we're going to show that little g big G is in G. That's pretty intuitive because both those elements are in G, and G is closed after all. So for sure that's going to be in G. So we're good there. G is closed. Gx is going to be in G. For the second part, we're going to take an element in G, and we're going to show that that can be written as G times big G. Can be written as G times an element in G. So we can write x as Ex, right? And E is just G inverse. Regroup, and bam, you've got G times an element in G. So that's in G big G. I think it's a cute little thing, but it's also important too. It's not just trivial, and it will come up again and again. And I will reference it, by the way. So, by the way, this is in G because, this is in G and this is in G. So the product is in G. So, anyway, GG is in G. I showed this to one of my friends and he just kept laughing because I kept saying G. Alright. So we got that. So we're good there. So let's keep going. So let's do another computation. This one's a little bit trickier. Find the order of the element in the factor group 2, 1 plus cyclic subgroup generated by 1, 1 in the factor group Z3 cross Z6 mod cyclic subgroup generated by 1, 1. Okay, so notice that G is Z3 cross Z6. That's our group. And our subgroup is a cyclic subgroup generated by 1, 1. Also notice that the size of G is 18, and the order of H is 6, and I showed that here. So what we're trying to find is the order of an element, and if you recall, the order of an element, that's the smallest integer such that we can take that element. It's the smallest power to which we can take that element to be the identity. So, like for example, like 3 in Z12 is order 4, because 3 plus 3 plus 3 plus 3 is 0, which is the identity in Z12. Okay, so, but here we're talking factor groups, so in our case we're trying to find the smallest m such that we can take our element to be the identity in our factor group, which is, remember, the identity in the factor group is the subgroup. And the answer is 3, because if we take this element, if we add it to itself 3 times, we get this plus this, which, if you can't see it, just write it on paper real quick. But 2, 1 plus 2, 1 plus 2, 1 is 0, 3. And this cyclic subgroup, doesn't matter how many times you add it to itself, you're going to get this. It's still the cyclic subgroup. And notice this is H. Since both of these are in H, when you add them together, you get you get H. And that again utilizes this fact that GG equals G, or HH equals H, or whatever equals whatever. So, hope that makes sense. So we're good there. Proof time. I should have written proof time number 1. We have 2 this time. So we have some really interesting ones these times, I'm telling you. So we're going to talk about a torsion group. And a torsion group is a group whose all the elements have finite order. And we just talked a little bit about that. What it means for the order of an element. Well, to have finite order, there needs to be an m such that you can take G to the m, take that element to the m, and get the identity. So that's what a torsion group is. And what we're trying to show is that if we have a torsion group, if G is a torsion group, then so is its factor group. Every time H is a subgroup of G. All normal subgroups of G. And notice this keyword here, every normal subgroup. If H was not normal, we would not have a factor group. So remember, the subgroup has to be normal in order for our factor group to be a group. Alright, so what's it saying? If G is a torsion group, we know what that means. We know that all the elements are finite. But do we know what it means for all the elements in G mod H to be finite? That means that the elements in G mod H, which look like this, they're cosets, that there's some power we can raise that to get the identity, which again is the subgroup. Well, let A be in G. Since G is a torsion group, there's some m such that A to m is E. And now we have H to the m. That means AH times AH times AH. Can't even say it, but hope you get it. M times. And notice that reduces just to AM to the H. Or, not to the H. AM, A to the M, H. Goodness. Like for instance, if you multiply these two together, it's just a squared h, and so forth. And as we showed before, a to the m is what? E, right? And EH is just h. So we showed that AH to the m is h. We showed that all the elements in this factor group are finite. It's a really cool one, and really don't underestimate it. I mean, I went over it in like 5 minutes or something like that, but really, if you don't understand it, you should really go back over it a couple times, because there's a lot of little details. And questions should be popping into your head, really. I mean, there are a lot of, I mean, like how to like real examples, like putting those letters to actual numbers, for instance. I always try to do that. I think it's really important. So here we got the second proof. This time we got a torsion-free group. Okay, I'm just going to stop talking. I'm going to actually read what I wrote. So a group is torsion-free if the identity is the only element of finite order. What we're trying to prove is that the torsion subgroup T of an abelian group is a normal subgroup of G, and G mod T is torsion-free in this case. So first we're going to show that if we have a torsion subgroup T that of an abelian group G, then it's a normal subgroup. So first we're going to do that. So what we got here? Just a setup here. Let G be abelian and torsion subgroup T. So we need to show that T is normal. And that's pretty straightforward. Let's just do that real quick. So T being normal, that means GT equals TG. So we take an element in GT, and since G is abelian, GT equals TG, which is in big TG. Thus, GT is in TG. And we use the exact same logic to show that the opposite is true as well. So we have T is normal. Alright, so now we have to show that the second part, so we need to show that G mod T is torsion free. So another way of saying that G mod T is torsion free, we say that, goodness, I can't spit it out. Alright, group is torsion free if the identity is the only element of finite order. So another way of saying that is if there's an element that's a finite order, then it's actually the identity. It's just another way of saying, and that's how we're going to prove it. Could have proven it by contradiction or whatever, and you can do that, it's fine, but this is the way I chose to do it. I think it's simplest, and I can do it all in one slide. So, alright, so we have an element in the torsion group, in the factor group, sorry, AT, and we want to show that if that's a finite order, then actually it is the identity. So we have AT to the m. Okay, so here's how we're going to start it off. We're going to say AT to the m. Well, again, that's A to the m times t. And if that equals t, as we showed that this equals t, if this equals t, that means that there's some element in t here such that this times this equals some element in t here. So I rewrote that. I rewrote this as this, when we're saying that t1 is in t and t2 is in t. But then if that's true, then we take t1 inverse on both sides, and we have a to the m is t2 times t1 inverse. And since this is obviously in T, since this is a subgroup and it's closed, then since that's equal to a to the m, then a to the m is in T. Since a to the m is in T, then a to the m is in our torsion group, so it's finite. So we can write a to the m to some power equals the identity. Since it's in our torsion group, we know it's finite, so we can write it like this. So if we rearrange it a little bit, we can show that a to the mk equals e. Just rewrite the powers there. So then we know that a is in our torsion group. But if a is in our torsion group T, then AT equals T, since both of these are in T. So we've shown that if there's an element in our subgroup that's a finite order, that actually it equals our identity. And again, this is another one where you might want to look over it a couple times. Honestly, I racked my brain on it for I can't tell you how many hours, but I really think it's a really beautiful proof. It's just all the little details, and there's a couple ways you can do it, but to really understand all the finer details, and with the set theory and how factor groups work and stuff, it's really cool actually, I think. All right, so what the heck did we just do? So this was the part that I really racked my brain on, trying to relate it to real examples of numbers. Is that if we have a group Z12, let's say. Well, all right, let's take what's the torsion subgroup of Z12? Well, since every element in Z12 is a finite order, then the torsion subgroup is itself G. So it's Z12. And so then notice that G mod T in this case is just the set containing Z12. It's a set of sets. Factor groups are sets of sets. And in this case, it just contains one set. So, in this case, our subgroup was Z12, and so that is our identity in our factor group. And since Z12 is, what am I trying to say here? To be torsion free, the identity has to be the only element that's of finite order. And since we only have one element, for sure it's the only element of finite order. So our factor group contains just one element, its identity. It's just another little tidbit. Okay, here's where I was making a mistake in my way of thinking. And I just put this here because I have a feeling that other people might have gone this route too, like mentally trying to think and made the mistake on trying to think of real examples using this idea of torsion. So I was thinking like this. I was thinking like, all right, how about we let take a torsion subgroup generated by 3. Since after all, this subgroup generated by 3, all the elements are of finite order. So it's a torsion subgroup of Z12. Well then, G mod T consists of cyclic subgroup generated by 3, 1 plus 3, and 2 plus 3. But since 1 plus 3 is finite, since if we add it to itself 3 times, we get the identity, then that kind of breaks our assumption that if for a torsion subgroup that G mod T is torsion free, since we found another element that's not the identity that's of finite order. But the problem here is that we're thinking is that the torsion subgroup is not the subgroup generated by 3. because the torsion subgroup consists of all the elements that are of finite order. So in this case, our torsion subgroup would be G, the whole group. So the issue is the initial assumption that let a torsion subgroup be the subgroup generated by 3, because that doesn't consist of the whole subgroup. Alright, so that's it for today. And let me know if you have comments, questions. Like I said, questions should be kind of popping into your head because this stuff is not easy, at first at least. So if you have anything you want me to expand on, just let me know. Alright, and good luck on finals.